So now let's get back to the work. Let's get back to interesting content. I have good news and I have bad news, as always. Um, the good news is we have a fantastic speaker, fantastic topic. Oh, and the bad news you see already. The bad news is that Tim Blazytko is not with us because he fell sick, but he is healthy enough to give the presentation. I think that is worth an applause already. So, Tim.
Thank you, guys. Can you hear me?
Yes, we hear you well. Before you start, Tim, give me a second.
All right.
So now you got the good news and the bad news. So the good news is, given that we had the Explain hack in Switzerland. I don't know, Tim, have you heard about Explain? I guess not, right?
I read about that, but I don't know really much.
Okay, good. That's fine. Essentially, what Explain was is a supply chain attack, right? So somebody was disrupting the supply chain, and of course, you can do this with open source components in the supply chain, which, well, at least in theory, you can look at. For binaries in the supply chain, it's much, much harder. And this is why the good news is that we have Tim as an expert to look into vulnerabilities of binaries. And I think, Tim, you're the founder of a company that deals with exactly this topic, right?
Yes, so basically I'm the founder of Mproof, where we build embedded security solutions for embedded devices.
Yeah, all right. Good, so then I would say the stage is yours, at least Teams, Microsoft Teams is yours. Thank you so much for joining nevertheless.
Thanks a lot for the invitation, and I'm really sorry I can't be here. I just went sick last week, and which makes travel currently not really possible. But yeah, still great to give the talk here. So today we talk about if we have given a binary, how we can identify or extract potential malicious behavior in these binaries. So I'm a reverse engineer since 15 years, and I also co-founded a company with some other guys in Bochum and the Netherlands, so in Germany and the Netherlands, where we design software protection schemes for embedded devices. And I'm also a trainer for code deobfuscation and reverse engineering techniques. And today we talk about a scenario which happens nearly on a daily basis, where we have an unknown binary and what we don't know, is this trustworthy? Can we trust it? Should we trust it? Or does it contain potentially malicious code or malicious indications? And today, we, from a reverse engineering or analyst perspective, we talk about some basic and some more advanced strategies, how we can cover or how we could tackle this problem. So the first thing is we start with some unknown binary. So let's say we don't know where it comes from. Maybe a friend is to us, a customer gave us this binary, we downloaded it on the internet or we bought it commercially, and we just want to know, are there potential backdoors inside? Or does the software contain any features which it shouldn't contain? So basically, what is malicious content? Malicious is like there's something additionally inside, like a feature, you don't expect it to be inside. Let's say if you are having a normal program and it encrypts all your files and sends it somewhere without your knowledge, this can be considered as malicious. If something records your keystrokes, your key, if you don't expect it to be, this is malicious. So depending on the context, malicious might mean the additional features inside that you don't expect to be the mix inside. So given a binary, where to start? So we have some very common approaches which at least are easy to perform and provide some good indicators about if the binary contains some behavior or not. So the first one is signature checks. A signature can be understood as a database of well-known crafted code patterns. And these code patterns might be known because we already have some signatures of existing malware or of existing malware features. And by providing a database of patterns like this rules.jar on top of here, we can then, for instance, take a tool like Jara, apply the rules, and then please apply these rules to the unknown binary and list everything you find. And then it might find something like, hey, there's some screenshot functionality inside this binary. Okay, if there's a screenshot or not, screenshot functionality inside the binary or not depends on the context, if this is expected behavior or not. But at least you can see, oh, there's some screenshot behavior inside. So there's a feature of potential screen capturing. Another example might be, oh, there are some cryptographic constants like SHA-1 or some encoding like CSC 32-bit. So maybe there are cryptographic algorithms inside. Or you could also learn like this is packed. So it's basically there's a code part or code sections which might be encrypted or packed in a specific way. So, however, besides the signatures, you can also dig a bit onto your own and look, for instance, for suspicious strings. So if you, for instance, check just the strings in the binary, you might see something like that. This is one example of a Chinese malware sample where we can see like, wait, there's some debug information left, like xplug keylogger.cpp or screen.cpp. If you see something like that, this at least looks suspicious. So it might indicate to be a program file, like source code, of some keylogging functionality or some screen capturing functionality. It might open also a shell or a telnet session, who knows? But at least finding something inside a binary might be suspicious. So there are also some other strings like HTTP or POST, which indicate some network behavior. The binary seems to or might indicate that it might open an HTTP request or send something. And here we see parts of an URL on a website like /update with some parameters. So by just looking at the strings, we might learn that it might indicate something like web-based behavior. So network communication. And then there's one last thing we can take a look at, and these are the API functions. So basically the functions which are used from the operating system, which are provided by the operating system to perform specific actions, like capturing keystrokes, or like opening a window, or just sending something over the network. So these are usually realized using API functions. And here, for instance, we can see that there are two libraries are imported, user32 and kernel32. And in these libraries, there are specific functions imported. So, for instance, like get key state or get async key state. These are library functions which are totally valid on its own, but they are also used quite often to implement keylogging functionality. So depending on the context, if you see something like that, that might be something to get suspicious, but it might also be okay. If you see something like that, where you think like find first file, find next file, you basically have some directory traversal or some file system access. And you also see like write file or create file, remove file. You can create files, remove files, and so on. So again, depending on the context, this might be totally valid. It might also be suspicious. However, if we see something like write process memory, this is something where really everything gets suspicious, because this means that we write some data into another process. And something like that is like in 9 from 10 cases malicious behavior, because we try to inject malicious code into other processes. So, but as said, with just some basic things, we can learn about the strings, we can learn about the API calls, we can learn about static signatures, and these already give us often a good overview about potential things which might go on in the binary. There's also one simple analysis one can do, which is called entropy analysis. Entropy is a mathematical computational algorithm which tells you how much randomness is in a specific blob of data. And the higher the entropy, the more likely, or the more likely it looks like random code. And this is something which can usually, which is often used in a malware analysis to check if there are specific code sections which are encrypted or packed. So what you see here is an entropy plot of the byte positions, like these are all the bytes of the binary sample, and this is the entropy. And the highest entropy is a value of 8. And here you see an entropy distribution of a normal, unobfuscated, unpacked file, where you see that most of the entropy is between 5 and 6, which indicates there's some sort of randomness, but still enough things, enough structured data to be not totally random. And you see there are also larger parts which have different entropy values. So this is basically something which can be considered as low entropy, and this is unpacked. However, if you see something like that, where most of the parts of the binary have a very high entropy, like close to 8, this is something which tells us, oh, there's a lot of random looking data, or a lot of data which isn't well structured. This is a good indicator for that there's packed or encrypted code. So in other words, high entropy means packed code. So to do a small recap, we talked about some basic methods to detect malicious behavior in binaries by looking at some signatures, by looking at the strings, the API functions, and the entropy. And I would like to take 1 minute to visualize that. So I have a tool here which is called Binary Ninja. This is a disassembler and decompiler. So basically, this is a binary analysis framework. And in Binary Ninja, I can, for instance, this is just one example, I can have something which is called triage summary, where I see on top of here, there I have an entropy plot. And here we can see this is all of the same color, more or less. So this is not encrypted. Down here, I see all the libraries which are imported, like kernel 32, user 32, and so on. Here in this window, I see some library functions which are imported. So for instance, like rec create key, this tells me that there's some functionality to modify the registry in Windows. There are some write files and some exit process, but also pass command line arguments and some other things. So basically, by looking at the API calls, I can still learn a lot. And then I have also a strings window. And in this case, I don't see any strings. And not seeing any strings in the strings window is suspicious. There seems to be some method in the code which hides the strings. So also not seeing anything in this case is an indicator that things don't behave as I expect them to be. Okay, so these are some basic things we can do. Looking for static signatures, strings, API functions, and the entropy. However, sometimes we need to dive deeper. We need to perform more time with a specific sample, or we need to manually reverse engineer it to check what's really inside. So the things before, this gave us good indicators which might be inside. However, sometimes we want to further verify that or confirm that, and then we do manual reverse engineering. However, reverse engineering, we sometimes have many thousands of functions of code locations we can look at. So the question is, how can we speed this up? How can we guide, or what can we use to guide our analysis process? And this is something where some heuristics came into the game. So, for instance, one heuristic is the identification of state machines. A state machine is typically a code construct which has the following form, where we have a large loop where a lot of different states, so-called basic blocks here, are executed in this loop, and then after we'll go back. You can think about it as this is state 1, state 2, state 3, and depending on some external behavior, like on a network process that we receive via network, we dispatch commands and go to this one, or to this one. So in other words, this is a loop-based dispatching routine, which is quite common in complex code. And in malware, these kind of functionalities often pinpoint like network protocol usage, but also command and control server communication and so on. So if you want to identify state machines like that, using a heuristic which pinpoints the graph layout of functions in this way is a really good way to proceed like that. Then there's another heuristic, which is called frequently called functions. The idea is, if a function like 0xdeadbeef is called a lot by lots of different other code locations, it must be somewhat important. So, and interesting or important functions to look at might be interesting because you learn a lot about the context, how the code is used. So, for instance, if we do this on some malware sample, on some embedded malware sample, which uses like the X or DDoS Trojan, this one has the most called functions like free, main copy, string length, and so on. You can see all of these functions are API functions like free some memory, copy some data, compute the length of a string, initialize some memory. So these are very often frequently called functions from userland code. However, in this scenario, we didn't really know what these functions are. And by looking that they are just called very often, and we can identify that these must be library functions. And therefore, we can add more context to that. Another example is the plugx malware family, where we have the most called functions are CRC2 32-bit and globe library R. In this case, remember some minutes ago when we looked in the imports of a file. Sometimes you have malware which hides the imports. If a file doesn't have any imports, it's also kind of suspicious. And in this malware sample didn't have any imports. However, these two functions here were used. This is basically a scheme called hash-based import hiding. They were used to compute hash sums and then check which files can be imported which match the hash sum. And this way, the frequently called function heuristic allows us to identify some important behavior of the malware, which is used for some very integral process, namely the importing of imports here. So, going a step further, XOR decryption loops. So, what you see in malware very often is that you have a simple loop which performs an XOR operation on some byte array with a fixed constant, like in this case 0xDE. So with a constant like that, well, this is not a secure cryptographic scheme. This is just something, this is the simplest form of encrypting some data that I can think of. And something like that, if you find something like that in code, it's most likely related to some malicious behavior because normal code normally doesn't do that. So in other words, if you start looking for XOR operations which use a constant and are computed within a loop, then this is something which might indicate that the malware does something malicious. Of course, it's just the existence of that doesn't mean anything, but it is at least an indicator to look further if anything else goes on. So these kind of loops are often used for string decryption routines in malware, but also to unpack code. And then one final heuristic, the RC4 crypto algorithm. The RC4 crypto algorithm is an algorithm which is basically totally unsecure and broken. So no normal application, like no non-malicious application, would ever use that in practice today. However, because it is so easy to implement, it is very, very common in malware. In other words, it is the most widely used cryptographic algorithm that can be found in malware. So in other words, if you can identify RC4, you have a good indication that that this malware might be worth a closer look. So question is how to identify malware. Don't get overwhelmed with that. Basically, we have RC4 has two functions, the KSA, the key scheduling algorithm, and the actual RC4 encryption. So two algorithms. However, especially one algorithm is very easy to pinpoint. It basically contains two for loops, like this one, and always uses a constant 256, so the maximum byte value. So in other words, if we look for functions which have two loops and use the constant 256, we have at least a good heuristic to pinpoint potential RC4 implementations. And these kind of things are often used for string decryption routines in malware, but also for domain generation algorithms, basically algorithms which compute the next domain, which will be contacted, like the CNC server, and so on. So to recap, in the first part, we took a look at some basic things, like looking at strings, looking at API functions, looking at the entropy. And in the second part, we talked about some more guidance, like if we have to get our hands dirty and dive deeper into the binary, we can use heuristics, which help us to identify potentially interesting applications specific to malware, like complex state machines, XOR decryption functions, RC4 implementations, and so on. So to conclude, the main takeaways are that binaries from unknown sources cannot be trusted. Well, this is no rocket science, but it's always good to repeat that. So common analysis techniques provide first insights, like first indicators. However, if you want to get sure, it's always good to have a closer look, do some manual analysis to confirm the initial indicators. And for the last step, so heuristics can guide analysis effort a lot. For many of the heuristics I demonstrated, I wrote a plugin, a Binary Ninja plugin, which implements these kind of things. If you should own the software, you can easily identify it. You can easily install it with a plugin manager. I would like to give a very short demonstration. So basically, I'm in this binary, and I have a lot of hundreds of functions here. Or let me take another one. I have another binary, and I also have a lot of functions here. And I don't know, is there something which might look like RC4? What I can do is, top of here, this will be my output window. I just query the plugin, like look for potential RC4 implementations. Then it prints some functions, and one of them tells me this might be case A. If I take a look at this function then, I see it has two loops. one loop on top of here, one loop here, and I see the constant 0x100, which is the hexadecimal encoding for 256. In other words, in this case, the plugin or the heuristic looked for functions which have two loops and also use the constant 100. We also see that we found another function which also has two loops and uses the constant 100 somewhere. So this one is, of course, a false positive. However, this one is not a false positive. So, and in this way, the heuristics, of course, are not always useful, are not always right, but they give me just 3 functions to analyze, which say this might be RC4. And just by looking at the function, then I can start deeper and deeper, look the context, how it is used, and stuff like that to identify, oh yeah, this is really RC4. And with something like that, the heuristics help pinpointing interesting behavior, which is often used in a malicious context. So thank you a lot for your interest. So to do a small recap, we talked about common approaches to identify malicious behavior in unknown binaries. Then we thought that manual reverse engineering to dive deeper is always a good thing, and that heuristics can guide the manual approaches. If you want to play around with that, feel free to check it out on your own. Otherwise, thanks a lot, and I'm open for questions now if we have time for that.
Thank you, Tim. Warm applause. We do have time for questions, and I guess there will be questions. Who would like to start? Benjamin. We have a microphone. Hold on a second.
Thank you very much for this interesting presentation. You showed very sophisticated ways to identify interesting routines to dig in. Could you elaborate a little bit how can you use this information with dynamic instrumentation to analyze what's actually done in the code, and what would you use?
Well, analyzing what's actually done is always a bit harder. This requires some more understanding. So basically, for instance, let me say in this case, I identified this function, that this is potentially interesting. Now I would start reverse engineering. I probably would start with looking at the decompiler output, like on a high level, on a C-like approximation level, to analyze what might this code compute, so to get a better understanding what this does. And then give it a name, like this might be RC4, here's A, and then analyze the context in which this is called, and so on. So this is a very deep process which takes a lot of time, but this is the way I usually approach it. Basically use heuristics to identify potentially interesting code constructs and then start analyzing them to check what they do. And if you were asking, you were mentioned dynamic scenarios. Well, if you have dynamic information, like you have an instruction trace where you know which code is already executed or not, it always provides additional information, because then, for instance, we can only have a look at the code locations which are really executed. Or we can also dump some register values and provide them into our static analyzer to get more context information and stuff like that.
Thanks, Tim. I have a follow-up one. Tim, assume for a second that we are all evil hackers in this room. And your task is not to teach us how to detect a binary, but to evade the detection. What number one tip would you give us? What hint? If we are about to write a binary, a malicious binary.
Well, there's a lot of things. So to keep it short, well, you can always hide things. Like you can apply obfuscation, you can pack code and stuff like that. Then you don't see the obvious ones. and you add basically different layers of obfuscation and encryption to make analysis as hard as possible. This prevents manual analysis, or at least it makes it a lot of harder. On the other hand, if you don't have any interesting strings, if you don't have any imports, this also looks suspicious. So what most APT malware does is it tries to look as normal code, as much as normal code as possible. However, lots of userland or mass malware tries to protect themselves using methods like that.
Okay, so it's again an arms race, and so we have to invite you again in 3 years to see where we stand. Thank you so much, Tim, for this interesting talk.
Thank you.
I do have chocolate for you, but you know chocolate is unhealthy, and as you're sick, it's not a good idea. We'll send it to you, so it will be there in 2 weeks, and then you can enjoy it. All right?
Okay, thanks a lot.
All right.
Enjoy the conference.
Thanks, Tim. Bye-bye.
Bye.